Bismillahirrahmanirrahim. We're beginning with the next chapter, which is network layer protocols. We'll be looking at three types of protocols: IPv4, ICMP, and mobile IP. In this video, we are looking at the IP protocol. Now in here, we have been given the summary of the functioning of the different protocols actually. So we have IP, which is responsible for making the packetizing, forwarding the packet, and for delivering the packet to the destination. However, IP does not do error control or recovery, packet recovery. It doesn't do that. If a packet gets lost, IP will not be bothered about it. It will just discard the packet and let it go. So for the error control mechanisms, we get ICMP. Okay, ICMP protocol accompanies IP. So while IP is responsible for the delivery of the packet, ICMP will look at error control. Okay, reporting errors to the source, error tracking, things like that. And then we have IGMP and ARP, which we will look in coming chapters. So these protocols are all the network layer protocols: IP, ICMP, IGMP, and ARP. Okay, so we're dealing mainly with the network layer. And you have to understand one thing about what's happening in the current internet scenario. Okay, we are having what is the situation at the moment. So in a device, you have the protocol stack. Okay, now this protocol stack, before it was something like this, right? So we had application, presentation, session, transport, network, MAC, and physical layer. Okay, MAC, physical, network or IP, right? TCP layer, session, presentation, and application. Okay, TCP or transport. But what's happening now with the different devices that are coming in? Now every device has got more than one interface, right? So you could have your phone which has 3G, Wi-Fi, Bluetooth, and then the USB. And in previous phones, you also had infrared, right? So you have different physical layer, MAC layer technologies. So nowadays, what's happening in every device is you have an expansion at the MAC and physical layers. Okay, you have an expansion. So right now, we are having right? So you're having something like this going on, okay? And we have an expansion at the MAC and physical layer, because now we are having different technologies, okay? So because we are having different interfaces in the devices, you're having more than one MAC, okay? More than one MAC and more than one physical layer, okay? This is what you're having. So you would have one for, let's say, Wi-Fi, 3G, okay, and then your 802.3 LAN, Ethernet LAN, and then you could have Bluetooth, okay, you could have USB. And each one of them has got its own physical layer, okay? Now, so even though we are having an expansion at these layers, we are still having one IP layer, okay? So the IP layer will look at how, so all these packets will go up to the IP layer. So the IP layer plays a very important role, okay, in having these technologies interacting, okay? So this is how it is. So before we had only one in here, but now we're having many, okay? So you need to remember this change that's going on. So the packets used by the IP are called datagrams, okay? They're called datagrams. And the datagram will have, it can have different lengths. It is variable length or changing length, okay? Packet, okay? So it's a packet, but it is a changing length packet. And it has two parts. It has the header and payload, which is data, okay? And now let's look at the header. So as you can see here, you have the header, which will be transmitted first, okay? This is how the packet will be transmitted. The header will be going first. And then you have the data, okay? Now let's look at the header. So this is the header of an IP datagram, okay? This is the header, all this. You have one row in this header of 32 bits, okay? This whole one row is 32 bits, which is 4 bytes, right? So this is 4 bytes in size, one row. Now, in the header, the first 5 rows are compulsory. They have to be there, okay? These rows have to be there. These are compulsory. If information in these rows gets corrupted, the packet will be discarded, okay? The packet will be discarded. So this is a very important set of rows. These are very important set of rows, okay? They are carrying the necessary information, okay? And what's the size of these rows? So it's 4 bytes into 5, which is 20 bytes, okay? So 20 bytes is the compulsory length of the header. It has to be there, okay? It's a compulsory length. And then you have an optional set of fields. Okay, this is the optional set of fields. It may be there, it may not be there. There are different types of information in the options field. We'll look at them in the coming chapters, hopefully. So now this options field plus the padding, okay? So you have to make sure that the IP header always ends in multiples of 4 because of the length being 4 bytes, okay? So this is why you need the padding bits to make sure at any time the packet fills until here. And what's the size of the optional field? 0 to 40 bytes, right? 0 to 40 bytes. So based on this options field and the 20 bytes compulsory information that's there in the header, the length of your header can be between 20 to 60 bytes. Okay? This is the length of your header. Minimum 20, maximum 60 bytes. And the total size of the IP packet, okay? So you have the header plus data or payload. Okay? So the total length is from 20 bytes if you only contain the header, all the way up to 65,535 bytes. Okay? So this will be the maximum length that you can have for an IP datagram. And this will contain header plus data. Okay? Now let's look at the different fields that we have in here. The first field is the version field, which is 4 bits. Okay? It's 4 bits. This will tell you what version is it. Is it IPv4? Is it IPv6? Okay, it will tell you the version. Next, you have the header length. And now pay attention to this one. Okay, you have the header length, which is also 4 bits. This field will tell you the size of the header. Okay, what is the size of the header? But because it's 4 bits, it will not tell you the exact size, but it will give you the size in multiples of 4. What does that mean? If your header length is given as 5, okay, if the header length is 5, then you don't take 5, you will have to multiply it with 4. Okay, so this will be 20. So 20 will be the actual length of the header. Okay, so anytime whatever value is given in the header length field, you multiply it with 4. This is how you get the value of the actual header length. And then you have service type, which will tell you basically quality of service. Okay, but in your syllabus right now, you don't have to, for this chapter, you don't have to worry about this field. We will look at it in the coming chapters. And then you have the total length. Okay, the total length. This total length will give you the length of the whole packet. Okay, the whole packet. Header plus data. Identification. Every packet will have a unique ID. Okay, a unique ID. And this ID is given to it by the source who makes this packet. Right? So, you have the source, okay? It is making packets, IP packets, okay? Every time it makes a packet, in here you will have a counter, okay? A counter. The counter will have an ID. Whenever a packet is made, the source will assign to it the counter value and then increment the counter by 1. Okay? So you will have a packet coming out 12 and then the counter will go 13. And then you will have a packet coming out 13, the counter will go 14. Okay? And so on and so forth. Okay? So the ID, and this identifier is unique for every packet. If this packet gets fragmented later on, okay, so if you have packet number 12 that got fragmented, every fragment will contain the same ID. This is for the destination to know, okay, what packet this fragment belongs to. And then you will obviously have the fragment number. Okay, so this is how things work. So this was about identification. Flag bits, we will look at it when we look at fragmentation. Fragmentation offset also, we will look at it carefully when we look at fragmentation. Time to live. Now the time to live field will contain the number of hops. Okay? It will, for example, if this is the source and this is the destination, and we have all these different routers in the middle. Now, we could have a problem where a source sends the packet, okay, but the packet, something gets corrupted, and the packet, instead of going to the destination, it keeps on going in the loop, okay? Some error has happened to the information, so it keeps on going in this loop. Now the problem with this is that you're having a stray packet, unwanted. It is just going there, increasing the traffic on the network, okay? So to avoid this scenario, this problem, we have, let's say if this is the route that the packet takes to the destination, when the packet starts at the source will assign it, let's say, a time to live value, which say 64. Every time the packet moves on to the next node in the network, this value will go down by 1. So when it reaches here, 63, 62, 61, 60, 59, and eventually 58. Okay, but here the packet is taken out. So if we are faced with this scenario of the looping, every time the packet goes into the loop, it will get decremented. And when this counter reaches 0, the packet is discarded. Okay? So in this way, we can prevent the internet from getting flooded with unwanted packets. So this is the function of the time to live field. Protocol, this will give you what type of protocol is above. TCP, UDP, okay, what type of protocol is being contained, ICMP, okay, it will give you the details in here. Header checksum is used for error control, as you know. And then you have a 4-byte IP address, 4-byte destination address. Okay, so you have the source IP and the destination IP. So this is the description of the IP header. So now we have different protocols, okay, that could be entertained. And these are the numerical values: ICMP 01, IGMP 02, TCP 6, UDP 17, OSPF 89. So these values, when you look at these values in the type field, you will know what type of a protocol this, or set of protocols, this packet is, or the datagram is carrying. Okay. Now we're looking at an example. An IPv4 packet arrives with the first 8 bytes as the following, but the packet is discarded. Why is that? So we have the first 8 bytes. If you look here, this will be version, and this is header length. Now the header length is 0010, which is 2. If you multiply it with 4, gives you 8. But is 8 the correct value? No, because we said the minimum header length should be 20. So this is why we know now that this packet has got some problem, and the receiver will discard the packet. In an IPv4 packet, the value of the header length is 100. Okay, how many bytes of options are being carried by this packet? So now the header length value is 8. So the total number of bytes is 8 into 4, or 32 bytes. Okay, we're multiplying it by 4. And we know, so what is it asking? It's asking for the options field. Okay, what's the size of the options field? Now we know that the compulsory field is 20 bytes. So whatever is remaining from after the 20 bytes will be the size of the options field. Okay, so we have 32 minus 20, which is 12. So the size of the options field is 12 bytes. An IPv4 packet, the value of header length is 5, and the value of the total length is 0028 to the base 16 hex value. Now it says how many bytes of data are being carried by this packet. So remember, this is to the base 16. So when you're converting this, okay, it will be 2 into 16 to the power 1 plus 8 into 16 to the power 0, right? So this is how you're converting the hex. And this is giving you 40 bytes. Okay, 40 bytes. So what is 40 bytes? Total length. Okay, the total length. And from these 40 bytes, how much is the header? 5 into 4, 20 bytes. 20 bytes is the header. So the data will be total length minus header length, which is 20. So it is carrying 20 bytes of data. An IPv4 packet has arrived with the first few hexadecimal digits, right? This is again hexadecimal, okay, hex values to the base 16. How many hops can this packet travel before being dropped? And the data belongs to what upper layer protocol? Hexadecimal, which means 2 digits represent 1 byte. Okay? 2 digits will represent 1 byte in hex. What is it asking us for? How many hops can this packet travel, which is time to live field. Okay? And where is the time to live field in the, here is the time to live field in the header. Okay? So it is in the 1, 2, 3, 4, 5, 6, 7, 8, 9th byte. Okay? It's in the 9th byte. So, considering this, you have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So these are the first 8 bytes, okay, until here. So this is the value which will tell you the time to live field. So it is again 1 into 16 to the power 0, which is 1. So it only has 1 hop left. If the next hop is not the destination, the packet will get discarded. And what layer will the packet belong to? What is the upper layer protocol? Sorry, the packet belongs. It is 02, and 02 we said was IGMP. Okay, IGMP. So it belongs to it's an IGMP protocol packet. Right? So this is how you solve these problems. Now, so this was the introduction to the IP packet. In the next video, we will look at fragmentation.